Hey guys, good night everybody. Just let me know if you guys can hear me before I start, please. Yeah, hopefully it'll be around that same time. Okay, so tonight I'm gonna be doing a past paper with you guys in physics. All right. We're gonna go through the solutions here. I want you to try to understand how we are getting some of these solutions. All right. Just let me know if you guys hear me. Yeah. Let me make sure you guys hear me before I continue. All right. So the paper I'm going to be looking at here is Jan 2016, right? This is the paper that I'm looking at here. So normally with my normal physics class, I would start with the latest paper and work backwards. So what I'm doing here, I'm doing papers that I have not really covered in my actual physics classes. Okay. So we have a motor car, travel from rest, and its velocity over an 80-second period was measured. The results are shown in the table. So what we have here, we have velocity, we have time, and we have some points that we need to label on this graph here. So on the grid provided, we need to plot this velocity time graph. Okay, that's what we want to do. We want to plot this velocity time graph. So first of all, let me get this table closer to the graph paper. Right, let's make sure you all are seeing the full graph paper, not blocking anything. Okay, good. All right, so we have velocity here, and we want to plot a velocity time graph. Okay, now the first thing you have to do when you're given question one is to decide on what scale you're going to use here. All right, so time is going on. Let's look back here. So they said plot a graph of velocity against time. Always look out for this word here. The word will be either against or versus. And the first variable here is going to be on your y-axis, and the second variable is going to be on your x-axis. Okay. So in this case here, you're going to put time on the x-axis. So let me just shift this a little bit here. Hold on. All right. So we need to decide on our scale here. All right. That's the first thing we need to do. You're getting marks for deciding on your scale. On the x-axis, we have to decide what we're going to use. Now, to decide what scale you're going to use, you're going to look at the smallest value, in this case here for time, and the largest value is 80 here. So we need to select a scale so that we're going to maximize use of the graph paper, right? So if I go 10, 20, 30, 40, 60. All right, so if we go 0, 10, 20, 30, 40, 50, right? 60. What do we get it by? 30, 40, 50, 60, 70. Yeah, we're gonna make it here, right? So we could get up to 80, right? And we need to label this. This is time in seconds. All right. Now, when it comes to physics, you are getting marks for selecting a scale. You're also getting marks for that's not just, yeah, for labeling your axes, right? So you're gonna get marks for labeling your axes. So make sure and put that inside here. And the thing is, labeling the axes, you all can just pull this directly from the table, you know. So that's 3 marks here once you follow what's happening on the table. On the y-axis now, we need to figure out how to maximize that scale there. So the smallest velocity is 0, and based on the graph here, the highest velocity here is 30. All right. So what can we do here? Let's see. If we go, can I maximize this by 2, 4, 6, 8, 10, 12, 5, 10, 15. could probably go every 4. We could probably put 5, 10. Can that work, by? I'm just trying to make sure we maximize the graph here, right? 1, 2. No, that won't work. Right, this could probably work here. All right, and let's label that axis there. Right, so again, you're getting marks for doing this as well, so you need to put V. So you're getting that information directly from here. That's V in meters per second. All right, make sure that's correct. 5, 10, 15, 20, 25, 30. Okay, good. So now we're going to start to plot the points here. So the first point here is going to be 0, 0. The second point here is going to be 20 against 30. So 20 against 30 is going to be up here, right? I'll label the points after. The next one here is 40 against 30. That's here. Next one here is 60 against 30. So that's here. And the next point here is 80 against 0. So we're back to here, right? So now let's join those points. In this case here, it looks like we're going to have straight line sections. All right, so that's the first straight line section. The next straight line section is going to be here. And the last section is going to be down here. All right, so this is a typical velocity time graph here. Okay, now let's label the points. They want us to label it A, B, C, D, and E. So this one here is A. This one here is B. This is C. This is D, and then the last point down here, that point is E. Okay, so far this is a very straightforward graph. All right. All right, sorry about that. I'm now seeing that there, right? Let me see if I can move the banner there. Hold on. Right, I'll take it off there for a sec, right? So you should be able to see there, hopefully now, right? All right, so that is part A of the question, right? Part A, they basically want us to draw the graph, right? Again, when you're asked to draw the graph, please indicate the scale. On my x-axis here, I'm using 2 cm to represent 10 seconds. So that's the scale on the x-axis. On the y-axis, I'm using 2 cm to represent 5 meters per second. Okay, so always indicate the scale that you're going to use. You're getting marks for that. All right, just for your knowledge, let me tell you what you get marks for here. So one, we get marks for the scale, right? So you get marks for the scale for sure. You get a marks for labeling your axes. All right, you get a marks for plotting the points. All right, so you do get a lot of marks for plotting the points. Sometimes you get 4 or 5 marks for plotting the points. Okay, let's move on to the next part. Use a graph to determine the acceleration in the interval AB. So where is AB now? So AB is that first section of the graph here. Now, what you can do, remember this is a velocity time graph. You want to get acceleration. Acceleration is simply the slope of the graph. So the first point A is given by 0, 0. The second point B, right, is given by 20, 30. right? So if you want to get the acceleration, acceleration is simply going to be equal to the slope of that line, right? So the slope of AB, which is given by this formula, y2 minus y1 all over x2 minus x1, right? That's how we find slope. So in this case here, what you can do, you can label those points, call this x1, y1, call this x2, y2, and then we're going to just substitute. So this is going to be 30 minus 0 all over 20 minus 0. Sorry. Right, so that's 30 over 20 or 3 over 2 or 1.5. And remember, this is acceleration, so it's going to be 1.5 meters per second squared. All right, that's what it's going to be, 1.5 meters per second squared. Okay. The next part, they want the velocity of the motor car after 70 seconds. And they want you to do this with the aid of dotted lines here. So you need to go back to the graph here, and we need to locate where 70 seconds is, right? I'm just trying to draw this a little better here. Maybe it's around here. Yeah, right? So to do that, you need to go up here, right? At 70 seconds, you need to go up to the graph. So you need to draw a line here. Right, so take a ruler, you draw a line here, and then all you're going to do, you're going to read off this velocity here. This velocity here corresponds to 15. So the answer for this part here is going to be 15 meters per second. So only have one more question. Okay. Now, the next part here, they want you to work out the total distance traveled in that 80-second period. Well, this is such an easy question here for 9 marks. Once you know your physics here, you guys can work this out very easily, right? Yeah, I saw somebody said you can use, so let's go back here for a sec. You see this part here with part 1, right? You can just work out the slope if you want, or you can simply use this formula here if you want. Acceleration is simply v minus u all over t. You could have used that as well. The final velocity in that section was 30. So it'll be 30 minus the initial velocity, which is 0, divided by your time. The time in this case is 20. So you could have worked it like this if you wanted as well, right? Either way, the answer is still 1.5 meters per second squared. Okay. Now this part here is like real easy here for 9 marks. This is a giveaway 9 marks. They want you to work out the distance travel in the 80 seconds. So remember, distance travel is area under your graph. Now you have 2 options here. Either you break up this shape into 3 sections if you want, or you can decide, you know what, I'm just going to work it out as the area for trapezia. Now some students can work it out that way. Some students have a little trouble. So I'm going to break it up, right? So I'm going to put a straight line here, and I'm going to call this area A1. That's a triangle. Let's drop our next line here, right? Now we have a next area here called A2. That's a rectangle. And then we left with this last section here, which is A3. Okay, so you have options, like I said. So the distance travel. So total distance travel, right, is equal to the area under the graph right, which is equal to A1, that's the triangle, plus A2, that's the rectangle, plus A3. All right, let's look at A1 now. If we look at A1 there, that's a triangle. So the base is 20 and the height is 30. So it's going to be a half by 20 by 30. So this is going to be a half by 20 by 30. So this is for the first triangle. The next part here is where some students might make a mistake. The height of this rectangle here is 30, but the base, and this is where you have to be careful here. This base here, you're going from 20 to 60, so that's 40. So it's going to be 30 by 40. So this here will be 30 by 40. So that's a rectangle. Plus we have one more triangle here, which is a half by the base of this triangle here, going from 60 to 80. So that's a 20. So it's going to be 20 by 30. right? So when you work this out here, half of 20 is 10, 10 by 3, 30 is 300, plus 4 3s are 1200, plus the same 300 again. All right, so that's going to be 306. So that's going to be what, 1800. Right? So again, easy 9 marks here. You can break it up into shapes, or you can decide, use a trapezium. Anyone you want it. Right? I see some people ask about chemistry. So unfortunately, we do have CAPE chemistry classes, but I'm not the one teaching the CAPE chemistry class. Right? I just don't have the time to pull it off. Right? All right, let's see what else we have to do here. So that's question 1. That's a very... No, I have an next part here. Sorry. All right, 2 more parts. So from your graph, describe the velocity of the vehicle in the period BC. So where is BC now? Right, so BC is this little section here. Now, they said describe the velocity. Now, in that section here, the graph is horizontal. So that means that the velocity is at 30. So what's happening there is that the car is traveling at a constant velocity, right? That's what's happening here, right? So that's all you need to say. For this here, you're going to just say the car is traveling at a constant velocity of 30 meters per second. Right? That's all you need to say. Part D now. This question investigated how velocity varied with time. Define velocity, right? Define velocity. Give me a lot of marks for this here. So velocity is simply the rate of change of displacement. Right? That's the definition you should give them. Right? And that brings us to our 25 mark question. Just a piece of advice here, guys. In question 1, right? In question 1, you should only spend about half an hour working on this, right? Half an hour working on this. Nothing more than this question at all. Even though it's 25 marks, in order to keep timing for the rest of the exam, only half an hour. Nothing more than half an hour, right? Right? People asking me if I merited in any CAPE subjects. So when I did A-levels, right? We didn't have CAPE. CAPE is something that CSEC introduced after. So maybe appearance. I would have done Cambridge. All right, I would have done Cambridge. And with respect to Cambridge, I did come first in A-level chemistry, right? So yeah, not CAPE though, Cambridge, right? All right, so let's move on to question 2. See what we have in question 2 here. You know, I've done so many papers over the years. Like, I don't remember ever doing this particular paper. This whole paper looks a little different to me. Like, I've never seen this paper before. Complete the graphic below by drawing an arrow to from each physical quantity to its respective unit. Okay, so let's start with density. So density is kilogram per meter cube, right? Moment, right? So CXC likes to bring these two words together here because they know students mix it up. So the moment of a force is the force by the perpendicular distance from the pivot. So in this case here, so let me just give you the formulas. So density is mass over volume. So therefore the unit will be kg over m cube. So that is going to give you kg m to the minus 3. So that's density. In the case of moment, So the moment of a force T is given by F multiplied by D. That's how you find moment. So that's the same as saying N multiplied by M. So moment is given by Nm. Now the next one here we have linear momentum. So linear momentum P is given by M by V. So that's going to be kg multiplied by ms to the minus 1. Now this is one unit that we could use for linear momentum, but there is another unit we can use. If you all remember your Newton's second law, it is written as mv minus mu all over t. If I cross multiply here, I will get that ft is equal to mv minus mu. All right. Now this on the right hand side here is your change in momentum. Right, that's your change in momentum here. So this unit on the side here is kg ms to the minus 1. But on the left hand side here, you have force multiplying by time. In physics, we call that impulse. Not on your syllabus, all right? If you're all doing Cape Physics, yes. But it is going to be n multiplied by s. So the unit that we're going to match up with linear momentum here will be ns. All right? That's what we're going to match up there. Right? So hope that making sense there, right? All right, so let's move on to so that's question 2 part A. What else we have here? All right, so we want to complete each of the following statements, right? We want to complete each of the following statements. So the first part here, they said kinetic energy is defined as what, right? So the kinetic energy is defined as the energy, right, possessed by a body right, by virtue of its motion. Right? So once an object is moving, it has kinetic energy, right? That's the definition for kinetic energy. Potential energy, right, is defined as the energy possessed by a body by virtue of its state or position. Right? Some of you all might be wondering, how come I didn't say it is just based on position? The thing is, we have gravitational potential energy. Gravitational potential energy is based on your position, right? So the higher an object is, the more gravitational potential energy it has. If you have, let's say, a spring and you stretch a spring, it has what we call elastic potential energy, and that is based on position. So since they didn't tell me gravitational potential energy, I'm going to say that it is the energy possessed by virtue of its state or its position. All right. The next part here, the formula for the change in gravitational potential energy. So your change in potential energy, delta EP, is equal to m multiplied by g multiplied by delta h. Okay, so that's the formula we use to find the change in gravitational potential energy. The next part here, waterfalls are commonly found across the Caribbean. Describe the energy changes that take place in the waterfall, right? So just picture a waterfall. Basically, we have water falling from the top of a cliff, right? This might be the basin here. So you have water at the top here. At the top here, the water is going to have gravitational potential energy. When the water falls, that energy is converted into EK, kinetic energy. So you're going to, the water is moving, so it has kinetic energy. You might hear a splash, so that is going to be sound energy. All right. So all we're going to do, we're going to say at the top, right, we have potential or gravitational potential energy. Right. Right, as it falls, right, what's going to happen is that we have kinetic energy now. Right, and then at the bottom, right, all of that kinetic energy is going to be converted into sound energy. Right, and we are also going to get some heat energy, small amount, but we're going to get some heat energy here. Right, so this is what's happening here in this scenario with respect to a waterfall. Right, let's see what's happening here now. Right, this next part here, we have a pendulum swings through from A through B to C and returns to A. So the starting point is here, then it moves to B, then to C, then to back to E. So A and C are the furthest points between, with B being the midpoint. State the type of energy, right? State the type of energy, right? Possessed or that exists at the point E. So at the point E, right? At the point E, what we're gonna have there is potential energy. Right? At the maximum point on a pendulum, the bob actually stops. So this here corresponds to your max EP. Right? That's what's happening here. Right? At the point A, that's max EP. At the point C, that's also max EP as well. Right? Maximum potential energy. Now, when the pendulum is moving though, right, the largest velocity is at the point B. So therefore, at B, that's your maximum kinetic energy. Right? That's your maximum kinetic energy here. And at the point C, we also have potential energy again. Right? So that's what's happening here. We have maximum potential energy. Right? Let's see what's happening in the next part. All right. Another point D situated midway between A and B. So let's go back to the diagram here. So you notice you have a point D here, right? That's midway between A and B. And I want to know if the pendulum is returning to A to complete an oscillation, explain which type of energy is increasing and why. All right. Now, if you think about it here, look at the position of where D is, right? D is at this level here. A is at this level here. They're telling us that this point D is, the pendulum is moving towards A. So therefore, what's happening here is that its vertical height is increasing. So what you're going to do, you're going to say at D, what type of energy is increasing? Your gravitational potential energy. Right? That's what you're going to say for this one. Right? And the reason, all you're going to do is the height is increasing right from D to A. Right, that's what's happening here. The height is increasing, so that's why the potential energy or the gravitational potential energy is increasing. Right, and the last part of this question here is this: netball is a popular sport played across the Caribbean. If a netball of mass that has a velocity of 5, calculate the kinetic energy. So kinetic energy is equal to a half mv squared. So this is going to be a half multiplied by 0.4 multiplied by the velocity squared, which is 5 squared. Right, I'm getting 5 joules. Right, so that's your answer there, 5 joules. Let's see what's happening in the chat. All right, so let me see what people are saying here, right? How do you know which papers to choose during crash courses? All right, so just for your knowledge, right? So I have my normal Form 5 class that would have started at the beginning of Form 4. So they are writing next month. And what we normally do, we start with the latest papers and we work backwards. So I would have started with Jan 2026 and work backwards with it. All right. Now, I know that I can only reach up to a certain amount of papers. So this 2016 here, I know I'm not going to reach to this paper. So that's why I'm doing this paper here. So that's my choice. That's why I decided to do this paper. All right. What people are saying here again. So here it is. When it comes to physics, you guys need to learn your definitions, right? You need to make sure you learn your definitions when it comes to physics. Also, try to make sure you practice as much calculations as possible. So when I'm doing my actual crash courses, I basically focus on the calculations that you all need to know for the exam, right? So those of you interested in attending my actual crash courses, I'll put up the information somewhere along the way, right? If you are interested. All right, let's see what's happening here. So that's question 2. All right, those of you who are in this class for the first time, please remember to hit like and subscribe for me, please. All right. Okay, so this question is about thermometers. Table 2 shows the type of thermometer, design feature, and reason for the design feature. Complete the table by inserting the appropriate information. So these are some of the thermometers we have to know for the exam. So the first one here is a mercury in-glass thermometer. And the first design feature is a narrow bore. Now, when we speak about a narrow bore, that's essentially the cross-section of that tube, right, that runs along the thermometer. So if I look at the cross-section, the bore could be like this. But when we speak about a narrow bore, what you're doing here, you're making the bore as small as possible. What that does, right, it allows us to detect small changes, right, or to detect small temperature changes. That's the purpose for this, right? Small temp. Right, that's the purpose of the narrow bore. Now the next one here, we have a constriction in the bore and it retains the measured temperature. So the only thermometer we know that does that is a clinical thermometer, right? So this is a clinical thermometer. right? That's the answer for that one. This third one here is a thermocouple. One of the key design features of a thermocouple is the fact that it can measure rapidly changing temperatures. If you all can't remember anything about a thermocouple, that's one thing you should remember. It has the ability of measuring rapidly changing temperatures. And the reason for that is that it has small junctions, right? It has small junctions. Okay. For those of you who don't know what a thermocouple is, it's basically, we have a galvanometer. We have two dissimilar pieces of wires, right? And what we're going to do here, we're going to create two junctions, right? We're going to create two junctions. So you have this. So you have one junction here and you have one junction here. But it's two different pieces of metal that we're using to create this thing. One junction, J1, is fixed. Normally it's fixed at 0 degrees Celsius. And this J2 here is what we're going to use to measure temperatures. Just recently, CSEC brought a question where we had to draw a simple diagram of a thermocouple. Okay. Next part here. All right, so they want us to define the upper and the lower fixed points on the Celsius scale and state their respective values on that scale, right? So we have two fixed points on your Celsius scale. So the first one is the lower fixed point. So the lower fixed point So your lower fixed point is actually 0 degrees Celsius, right? So they access to the temperature, so you need to give the temperature, right? Now, what is it? It is the temperature right, of pure melting ice. That's what it is. Temperature of pure melting ice. Right, that's the definition here for the lower fixed point. Next thing here, we need to know the upper fixed point. Now, the upper fixed point is taken as 100 degrees Celsius, right? And this is the temperature. Right, of steam above pure boiling water. Right, so that's my definition for my lower fixed point and my upper fixed point. Okay. What else we have here? Right, have this and what else? All right, so figure 2 shows a sealed flask which contains a fixed mass of gas held at constant volume. All right, so you have a fixed mass of gas and it's at constant volume. So first thing, when you all get these kinds of questions here, we need to understand which gas law are we talking about. So in this case here, volume is being held constant. So therefore, this is going to be the pressure law, right? Volume is being kept constant. So it is the pressure law that we're dealing with here. Now, for the pressure law, we have pressure is directly proportional to your absolute temperature, or we can say that pressure is equal to K multiplied by T. Now, this is one way of expressing the pressure law, or we can say that K is pressure over your absolute temperature, right? But normally when we use any pressure law, we normally use it like this. P1 over T1 is equal to P2 over T2. Okay, this is typically how we use the pressure law. Now in this question here, this is what they said. When heated, the temperature and the pressure of the gas, right, increase as shown below. So we have pressure 1.1 by 10 to the 5, 1.2 by 10 to the 5, 1.3 by 10 to the 5. And they give us temperatures. They want us to complete the table because we want to convert the temperatures into Kelvin. So if you want to convert to Kelvin temperature, right, the formula that we're using here is this. Kelvin temperature is equal to your Celsius temperature plus 273. So basically, every single one of these temperatures here, we're going to add 273. So 35 plus 273, we're going to get 308. So this here is going to be 308. The next one here will be 63 plus 273. That's 336. Right? And the next one here is 91 plus 273. And you're going to get 364. All right, so easy 3 marks here. All we're doing here, we're converting all of the temperatures from degrees Celsius into Kelvin, right? Somebody said freezing point for the last question. No, you can say freezing point, that's fine. Nothing wrong with that, right? The freezing point is also the melting point. All right, now when this question actually came, I remember students saying that they weren't sure how to answer this question here. Right? They weren't sure how to answer this. So they said, is the pressure law supported by the data? Now what's happening here is that we have pressure and we have temperature, right? So remember we just said that pressure is equal to K times T, or you can work out this constant here and basically say pressure divided by a temperature. So let's do that. So let's work out K for each of the values that we have here. So K is P on T. So the first value we have in the table is 1.1 by 10 to the 5. So it is 1.1 by 10 to the 5. And we're going to divide that by 308. So this is going to be 1.1 by 10 to the 5 divided by 308. All right, 308, yeah. So what I'm getting here, I'm getting 357. Right, so that's for the first row of data. Let's work out K again for the second row. Let's get P on T, and let's see what we get. So for the second row, you have 1.2 by 10 to the 5, and you have 336. So it's 1.2 by 10 to the 5, and we have 336. Okay, so 1.2 10.5 divided by 336, and I'm getting 357 again. Right, so we're looking like we're gonna get a constant here for all of them. So the last one here is P on T again. So that is gonna be how much? 1.3 by 10 to the 5 all over. In this case here, it is 364. .3 by 10 to the 5 divided by 364, and we get 357 again. All right, so CXC says, is the pressure law supported? Right, so all you're gonna do is say, since, right, K is a constant, right, in this case a constant of 357, right, the pressure law is supported. Right? All right, so that is that's number third one. Okay, this next part here now. All right, this part here, the angle of incidence is equal to the angle of reflection. This is one of the laws of reflection. So we're talking about reflection here. State the other law. All right. So the incident ray, you need to learn this. The incident ray, right? The just give me 1 second, guys. Right. So I'm back. I'm back. Don't worry. I just step out for a second. So the incident ray, the reflected ray, right, and the normal all lie in the same plane. Right? So basically, this is what's happening here when it comes to law of reflection. So basically, we have our incident ray here. This is your normal, right? Then you're going to have reflection taking place here. So this is reflected ray. This is your angle of incidence. And this here is the angle of reflection. Okay? And this is your plane surface here. So there are two laws of reflection. One is the angle of incidence is equal to the angle of reflection. So I is equal to R as 1. And then the incident ray, the reflected ray, and the normal all lie in the same plane. Okay, that's the answer for that one. Now, the next part here, they said state 3 properties of the image produced in a plane mirror. So every morning when you wake up, chances are you look into a mirror, right? So in terms of properties, one, we have lateral inversion. So the image is laterally inverted, right? So if you hold up your right hand, it looks like your left hand in the mirror. That's one, right? The next one here is that it's a virtual image. So it's virtual, right? So the rays don't actually pass through, right? The next property here is that it is upright. So when you look at yourself, if this is your head, what you see in the mirror is also going to be your head. You are not inverted in any way whatsoever. So it stays upright. You can say that your object height, or the, sorry, we're talking about the images, right? So the image height right, is equal to object height, right? So that's true. Also, we can talk about the image distance and object distance. So image distance right is equal to object distance. Right? There's one tree. If I had to give tree here, I'll stick to this one, and probably this one. That's it. Okay. What else we have here now? It's part B, some kind of mirror question. Somebody's asking about human and social biology. No, we don't have that. We don't have that. Right? We just have biology by itself. All right, figure 3 shows a car located 5 meters behind a truck, which is 8 meters long. Assume the external mirror of the truck is a plane mirror and is in line with the front of the truck. All right, it's in line with the front of the truck. Calculate the image distance. Calculate the image distance of the car as seen by the truck driver. Right? So you want the image distance of the car as seen by the truck driver. All right? Now, the only information we have there, right, will be if this is the car here, right, and the driver is inside, right, the driver is going to see in this mirror here. That's what the driver is going to see. Well, all we need to do is to add the 5 meters plus the 8, and we're going to get 13. Right? That's as much as we can do there based on what they have. Right? So that's the image distance of the car. Okay? So that's part 1. All right, this next part here states a reason why the sign shown in figure 4 is more likely posted at the back of the truck rather than a car. All right, so sometimes they bring questions where they try to make it as practical as possible, right? So in this case here, right, how are we going to answer this part here? Okay, so the thing is, light will travel in straight lines, right? Light will travel in straight lines. So if you go back here, now the car, the only way the driver is going to see the car, right, is if the driver is in line with this mirror here, okay? If he's at the back of the truck, the truck driver is unable to see him. So light needs to reflect off of the car, off of this mirror here, in order for the driver to see him. So the question is saying, state with a reason why the sign shown is more likely posted at the back of the truck rather than a car. So remember, the truck cannot see behind here at all. This is like a blind spot. The truck cannot see that at all. So in order for the truck to see, whatever object it is, which in this case is a car, must line up with the mirror in order for the truck driver to see, right? So that's the reason. Light travels in straight lines, so the car must line up with the mirror in order for the truck driver to see it. In the case of the car, a car doesn't require something like this, because inside of a car, you have the rear view mirror, so the driver can just look in the rear view mirror and they can see what's happening behind the car. All right, so that's all we're going to say for that part. What else we have here now? We have some fun refraction calculations. All right, we have this, and what else we have here? All right, so a ray of light passes through a block of material as shown in figure 5. Okay, so we have a ray of light starting from here and it enters a block of material. Now they said if the refractive index of the material is 1.3, calculate the angle of refraction in the material given that the angle of incidence is 30 degrees. So what they're really asking us to calculate is this angle here. That's what they want. Okay. So to do that calculation, we're going to say that refractive index N is given by sine I over sine R. So we're going to say 1.3 is equal to sine of 30 degrees divided by sine R. So first thing we're going to do, we're going to put 1.3, we're going to put that over 1, and then we're going to cross multiply. So 1.3 by sine R is equal to sine 30 by 1. So in this case here, we're going to see that 1.3 sine R is equal to sine 30. So therefore, sine R is equal to sine 30 over 1.3. So therefore, sine R is equal to, so sine 30 divided by 1.3 is right, so that's 0.385. So therefore, R is arc sine 0.385. So R is equal to, I'm getting 22.6 degrees, right? So that's my angle of refraction into this material here, right? 22.6 degrees. Right? All right, let's see what else we have here. They said if the refractive index of the material is increased, why would the lateral displacement of the ray increase? Now, first of all, here's what's happening here. When you have a rectangular block, whether it's glass or ice or anything like that, and you have a ray that is doing this, let's say you have a ray that enters here. First of all, the ray is going to bend, and it's going to bend like this, right? But when it leaves, it is going to exit here, all right? So what's happening here is that we have what we call lateral displacement. So some of you all may have done this as an SBA lab in school. So this here is your lateral displacement, right? That's what we're talking about it. So the ray initially traveling in a particular direction, it is shifted. It is laterally displaced, okay? And what the question is asking is that if the refractive index of the material is increased, why would the lateral displacement of the ray also increase? Well, if you think about it here, right, you're going to get a greater, so you're going to see there will be, right, a greater angle of refraction right? And therefore, a greater lateral displacement. All right, this is a 1 mark something here, so okay. So that takes care of number 4. Let's see what number 5 is. This is kind of strange though, because they had the first question 4 is based on ray optics, and question 5 is also based on ray optics. It's odd. All right, so a convergent lens can be used to form a real or a virtual images with reference to the focal length of a lens. Describe the object distance required to produce each type of the following, right? So one of the things you all have to know for your exam, so what kind of lens are we looking at here? Convergent, right? Convergent lens. So there are basically 3 diagrams you all need to know for the exam, right? So if this represents my principal axis, right, and this is my lens, you have F, right? You all need to know these diagrams, by the way. So this is F, this is 2F, this is F, this here is 2F, right? And this is center of the lens. So one of the things you have to be able to know is that when I place an object between O and F, right? Let's say I put an object here, and I want to locate where the image is going to be. What's going to happen is that you draw a ray parallel to the principal axis, and if it does that, it is going to pass through your focal point, right? Then you have to draw a ray that is passing through the center of the lens, and when I extrapolate this here, what's going to happen is that I'm going to produce an image, right? And this here is going to be your image. So that's scenario 1. How do we get, in this case here, you're getting a virtual image. So if the object, right, so the object between, right, O and F, that's the center of the lens and the focal point, right, then you create a virtual image, right? So a virtual image is created. Right? So this is one scenario here. What CSEC can ask us to do is to draw this diagram. They could also ask us to give an example where this happens, and this happens in a magnifying glass. If you want to magnify an object, just place the object between the center of the lens and the focal point, and the image produced is going to be magnified, right? Now, if we want to create a real image, right? Did this say what it is? Okay, you just want a real image here. So for the real image, all we need to do right? Again, label your center of your lens. This is your focal point. This is your focal point. This is 2F, and this is 2F, right? Now, if you put an object between F and 2F, right, what's going to happen is this. If we draw a ray parallel to the principal axis, then the ray is going to do this, right? It's going to pass through the focal point. These are just sketches, eh? I mean, you have to use ruler and stuff to work this out. In this case here, let's pass through, right? So you're gonna get an image. So the position might be wrong because I'm just sketching here, right? But what you do get, you're gonna get a real image here being produced, right? So object, right? In this case here, it'll actually be beyond F, right? Anything beyond F will give us a real image. Right? This is something that students may or may not remember in the exam. Okay. Now, the next one here, they said state the orientation of each of these things here, right? Each of the image produced. So in the first one, the image, right? So the virtual image, right? It said orientation, right? It said orientation. So in this here, the virtual image is upright, right? And for this one here, right? Now you kind of have in this one the real image, is inverted. Right, that's what's happening here. So the virtual image is upright, but the real image is inverted. Okay. All right, let's see what happened here now. Right, so they want us to complete this diagram here. Now this diagram here is for a divergent lens, right? Right, let me see what you all saying. Some of you all, I'm not reading the chat here. Some of you, by chance, somebody said something about infinity there. I know they removed it here. Right, so it depends on where you put it, right? Based on the question here, you just have to go beyond F to create that real image, right? Somebody's asking about chem. So honestly, it's when I have time, right? I will try to go live for this whole week here, but we'll see. Maybe I'll do some chem tomorrow. Maybe I'll see. All right, I kind of have to see how my schedule is running. Okay, so we have a divergent lens here. So to work with a divergent lens, what is supposed to happen is this. The ray is going to depart like this, right? Right? But what we need to do, we need to extend this here to pass through the focal point, right? So you all need to know how to draw this diagram. This is for a divergent lens. When I extrapolate the ray backwards, it should pass through the focal point of the lens, okay? All right, this next one here. Calculating magnification where a lens produces an image height of 3.6 for an object 2.4 millimeters in height. So you want to get magnification. So magnification is given by your image height over your object height. So in this case here, the image height is 3.6 and the object height is 2.4. So therefore, this is definitely an enlargement. So this is going to be 3.6 divided by 2.4. And you're going to get a magnification of 1.5. That's it. All right. So I find they're giving us plenty marks for that though. Right. Now they said for the same magnification, calculate the image distance given that the object distance is 20 cm. So the second formula for magnification is this. It is given by image distance over object distance. Now we want to calculate image distance. So you're trying to calculate what V is. So V is simply going to be M multiplied by U. So we're going to take that magnification of 1.5 and multiply by U, which is 20. So that's 1.5 by 20. So that's going to give us 30 cm. Okay. So that's going to be your object distance. Okay. So basically, we have an object, right? Let's say this is our object here, right? This here is our lens, right? What's happening here is this is going to be your image, but this distance here is 20, right? And this distance here is 30 cm. That's basically what's happening here. Right? So there is a magnification taking place because the image distance is bigger than the object distance. What else do we have here now? Last part of the question is to calculate the focal length of the lens. Now make sure you all know the lens formula, right? Make sure you know what the lens formula is. So you want to calculate the focal length of the lens. Lens formula looks like this. 1 over F is 1 over U plus 1 over V. All right. So 1 over F is equal to 1 over U, which is 1 over 20, plus we calculated V as 30, so 1 over 30. So 1 over F is equal to 1 over 2 plus 1 over 20. Right? And I'm getting 1 over 12. Now, some students, they make a mistake and they stop right here. That's not the correct answer. We still need to calculate F. F is going to be equal to 12 cm. Right? That's the value for F here, 12 cm. Right? And we just have one more question here. All right. So scientists use symbols when dealing with circuit diagrams in electricity. An electric circuit is displayed in figure 7. Write a description of the circuit in the space below. Okay, so you have to look at this diagram here and you have to explain what's happening here. So there are several things we can say. So we can say battery, right? That's this guy here. Switch, right? We also have a variable resistor, right? What else we have here? We have a fixed resistor, and an ammeter, right, are connected in series. Right, connected in series. Then we have a voltmeter here. This voltmeter here is connected in parallel across the fixed resistor. So you're going to see that a voltmeter is connected in parallel with the fixed resistor. Right, so I've described the circuit as seen here. I've indicated everything that is in the circuit. So they gave them 6 marks for that, yes. Wow. Right? Yeah, somebody said the switch is open. Yeah, you can say that. Let me go back to the diagram. Yeah, that's true. The switch is open. Yeah, that's true. Anything else you all seen? Right, because 6 marks here, so as much information as we want to give, we should. We could also say that the EMF of the battery is 3 volts. Right? Because the 6 marks here, we need to give as much information as we possibly can. Right? Right, so thanks for the extras inside here, right? Thanks for the extras, right? The switch is open, right? Thanks for that. And well, the EMF of the battery is 3 volts. All right, let's go back here now. A physics class was given a circuit diagram as shown in figure 8. use figure 8 to answer the 3 questions posed to the class. So given that the formula for the equivalent resistance R1 and R2 is given by this formula, so what they've done, they've given us a formula to use here. So we want the equivalent resistance between here and here. So that's this 1 ohm in parallel with this. So we're just going to use the formula as is. So R1, R2 will be 1 multiplied by 2 all over 1 plus 2. So that's going to be 2 divided by 3. So we can leave it as 2/3 ohms, right? Or you can say 0.667 ohms, right? So that's a 2 mark there. Right? What else we want here? We want to calculate I want to calculate the current flowing in the closed circuit. Okay. Now, here's what's happening here. When this switch is closed here, right, what's happening here is that we have this combined resistance, right, which is 2/3 or the 0.667 in series with this. So once the switch is closed, what's happening here is this. Your total resistance in the circuit will be equal to 2/3 or the 0.667 plus that 3 ohm resistor there, which is actually 3 2/3. Right? So that's the total resistance in the circuit when the switch is closed. Now we want to know the current flowing in the circuit. So I is equal to V divided by R. So the voltage in the circuit is 12 volts. Right? So you have a 12 volt circuit here. So it's 12 divided by 3 2/3. Right, and I'm getting 3.27 amps here. Right, that's what I'm getting, 3.27 amps as the current that is flowing in this circuit. Okay, and the final part of the question, when the current in B part 2 flows, what is the power dissipated in the 3 ohm resistor? So let's go back here again. So the current flowing through this resistor here, right, that 3 ohm resistor is that 3.27. So this current I here is 3.27. So what we're going to do to work out power dissipated is given by I squared R. That's the formula we're going to use. So the current is 3.27. So this is going to be 3.27 squared multiplied by the resistance, which is a 3 ohm resistor. So when we work this out here, we're going to get 3.27 squared multiplied by 3. And we're going to get about 32.1 watts. Right? So that's the power dissipated in this resistor here. Okay? All right, just for your knowledge, in terms of electricity formulas that you need to know Ohm's law, which is V is equal to IR, right? You need to know that Q is equal to I by T. That's a formula we need to know. We also need to know that V is equal to E on Q. That's a formula students generally don't remember. When it comes to power, we have power is equal to I by V. We also have power is equal to I squared R. And we also have power is V squared on R, right? So these are all our formulas that we need to know for electricity, right? These are formulas that you all should commit to memory. Make sure you know them, right? All right, guys. So this brings us to the end of this Jan 2016 paper, right? So 90 over 130. How much is 90 over 130? Multiply by 20. It could work. It could work. That's about 13.8 out of the 20. It's possible it could work, right? One of the things that can bring up your marks for physics is the multiple choice. Try to do as many multiple choice papers as possible. They're gonna repeat a lot of them, so try your best, right? All right, people are asking when am I going live? So I will try to come live during the week again, around the same time. 8 o'clock is the time, right? So just look out for around 8 o'clock. Power is I squared V for transform. No, it's not I squared V, it's still I squared R. Power is IV for a transform. Right? Power is IV for a transformer. All right. So guys, this is all the time I have for now. Right? So thank you for coming. Right? Please remember to hit like and subscribe. Give me 1 sec, right? Give me 1 sec. You all wanted to find out about the crash courses. I have it here. Or is it gone? 1 sec. Should have it somewhere here. Right? I know some people wanted to know the dates. So basically these are paid crash courses though, right? And it's either Saturday or Sunday, and it's generally like from 9 to 4, right? So it is a long session, right? Right? Hold on 1 second. Right? So again, if you are interested, right, these are the dates for my crash courses, right? These are the dates. All you need to do is send a WhatsApp and I'll send you the information, right? But I will be having a crash course for maths, chemistry, as well as physics, all right? For chemistry and physics, I typically go through the entire syllabus again. I focus on what is required. For those of you who don't know, I do mark chemistry, right? So I do understand how the paper is actually marked. In 2024, we had students who made it to the merit list, as well as 2025 in chemistry. All right. So if you are interested, my chemistry crash course is available, as well as the physics, maths, and the maths. All right. All right, guys. So this is the number here. Just send a WhatsApp to this number here if you are interested. All right. So guys, this is all the time I have. So enjoy the rest of your afternoon. Be safe, right? And I'll see you guys hopefully during the week again, right?